Mba633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we will draw on our knowledge of simple linear regression to have a conceptual introduction to multiple linear regression. See in what respects they are similar and also how they are different. The general objective of multiple regression is to study further the relationship between one dependent variable and several independent variables. Now, the simplest relationship that one could hypothesize between one dependent variable and a collection of independent variables is a linear relationship, and that is what gives us the term multiple linear regression. Now, if you look at the example in front of us here, we have data on a bunch of football teams, and this is presumably for one season. So the first column that we have here is the winning percentage of each of these teams, and then following that we have a number of variables. For instance, in column D we have interceptions taken away, column E is fumbles taken away, column F is interceptions given away, column G is fumbles given away, H is defensive yards per game, I is rushing yards per game, J is passing yards per game, and K is field goal percentage. So just to keep things shorthand, we will label these independent variables x1 through x8. So we have 8 independent variables, and we want to study, explore further what kind of a relationship might exist between y, the winning percentage, and these 8 independent variables. So if we hypothesize a linear relationship between this set of 8 independent variables and the y, then the equation that we have is equation number 1. So we are positing that y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 all the way to beta 8 x8 plus an error term epsilon. So x1 through x8 were the 8 independent variables that you saw in the previous worksheet. And notice that this equation is for the population. So what population are we talking about? So in order to estimate their betas, beta 0 through beta 8, if you think about it, I really need data on all games for all these teams throughout all time, in fact. However, I have data for only one season, so the data that I have, the one that you just saw in the previous worksheet, is sample data. Okay, so I really cannot be computing the betas. Instead, using the sample data that I have, I would fit not a straight line in this case, we would fit what is called a hyperplane, since there are 8 independent variables. Once you get beyond 2 independent variables, it's very hard to sort of visualize mentally what the surface looks like that you're fitting through the data point, but in mathematical terms what we are fitting is a hyperplane. So we fit this hyperplane through the raw data that we have for these teams, and remember this is sample data. We get an estimated equation just like we did for simple linear regression. So the expected value of y is b0 plus b1x1 plus b2x2 and so forth up to b8x8. So as in simple linear regression, the error term, because these 8 independent variables will not be able to predict y absolutely perfectly, there will always be some kind of an error term, larger or smaller, but usually there will be some error left over. Okay, as in simple linear regression, an assumption is made that this error term e is normally distributed with a mean of 0 and a variance of sigma squared. Hence, the expected value of y, that is once we get from the estimation with the actual data that we have, is b0 plus b1x1 and so forth up to b8x8. Therefore, if you look at the b's are point estimates of the corresponding betas. So b0 is a point estimate of beta 0, b2 is a point estimate of beta 2, b8 is a point estimate of beta 8. Why point estimate? I don't have data on all the games that have been played. I'm only looking at data from one season, so I'm looking at sample data. Hence, it's what I have. This b0 through b8 are sample statistics. Okay, so you remember from simple linear regression, that in addition to these coefficients B0 through B8 that you would get from Excel when you run the regression, 99.9% the rest of the output from Excel is simply there to tell you the quality of this fitted line. In other words, is the regression statistically significant or not? Now, up to now, the discussion that we've been having is fairly similar to the discussion that we had for simple linear regression. But now things start to diverge a little bit in terms of testing for the significance of the regression. Now, when you have one independent variable like you did for simple linear regression, if the regression is not statistically significant, then the one independent variable that you're using is not statistically significant either. You can't have a contradiction there in the sense that the regression is significant, but that one independent variable is not, or vice versa. Okay. Now, for multiple linear regression, the situation in terms of deciding whether the regression is significant or not is a little more complicated. So there are two sets of tests that we do. So you look at this null hypothesis over here, H0, beta 1 equals beta 2 equals beta 3 equals beta 8 equals 0. So my nightmare scenario is none of these 8 independent variables that I have chosen have any relationship collectively. So collectively, these 8 independent variables that I have chosen do not have a relationship with y. So all these slopes are 0. So I'm plumb out of luck. So I really cannot use this relationship to predict y. So the first test that I want to check is, are these 8 independent variables collectively, are they statistically significant? Meaning, if I use all 8 independent variables in this particular equation, do they tell me anything about the dependent variable y? So that's the first test that I do. And if you remember from our discussion of the test of means of multiple populations, I think you can guess how this test would be done. This test would involve some kind of an ANOVA test. We'll see that when we run our Excel. But if the result of this first hypothesis test is that I reject the null, then I can safely conclude with a fairly high degree of certainty that one or more of these independent variables that I have chosen are contributing to explaining y. So they are doing their part in explaining y. So the alternate hypothesis is not all slopes are 0. So if I manage to reject the null here, then I can conclude with a fairly high degree of certainty, whatever my significance level is, that, well, some of these independent variables are in fact helping to explain the dependent variable y. But that's not enough. What you could have here is that this collection of 8 independent variables collectively together are in fact explaining y, but not all independent variables are equally significant. In other words, one or more of these independent variables could really not be doing a whole lot towards explaining y. Therefore, in addition to this F test, this collective hypothesis test that we have over here, we would, in the case of multiple linear regression, we also have separate individual tests for each one of the slopes. Okay. And what is entirely possible is that you could collectively, the regression could end up being significant, meaning all independent variables, these 8, when you use them collectively, they do in fact, as a whole, as a group, they can do a good job of explaining y. But not all of these independent variables contribute in the same manner. One or more could be hangers-on, so to speak, and they are not individually significant. So you have a collective test and individual test. That's a major difference in checking the significance of multiple linear regression. And that begs the question, okay, if collectively these 8 variables are significant, but individual tests show that one or more are not, then can we make the model more parsimonious? So as we develop our discussion of multiple linear regression, we will see how to build on these diagnostics, or how to use these diagnostics to try and get a parsimonious multiple linear regression model. A parsimonious model would be one where informally you have just as many independent variables, just as barely necessary. You don't have any more than you really need, meaning all of them are pulling their own weight, are contributing to explaining y, so that even though collectively these independent variables, maybe explaining the dependent variable well. Each and every independent variable on its own has some contribution to make, and there are none of them that are just hanging around not contributing to the explanation. So you have a collective significance test as well as individual significance test. That's sort of a major difference between multiple linear regression and simple linear regression when it comes to understanding the diagnostics that Excel generates. Okay, so in the next couple of video segments that we have, we will actually run the regression in Excel and look at the output and try and understand what those numbers mean, and then from there see what the collective and individual significance tests lead us to in terms of building a slightly more parsimonious model of predicting the winning percentage for these football teams.